Alrighty. Good afternoon, guys. My name is Dylan, and I'm an undergraduate, and I've been working with HPRC for a couple years now. So I'm pretty familiar with the LSF job scheduler. I work at the help desk. Well, I worked at the help desk when we had a help desk, and now since the coronavirus, we've been working remotely. So I have not actually been to the help desk in a couple months now, I guess, since March, around March. But I normally also help out with the short courses and stuff, including these primers. I've been teaching like Linux and um, I've been teaching Linux. I do database data management, and then now that we have these 1 hour kind of like primers on the job schedulers and the clusters, I've been doing those. So today we're going to talk about the LSF job scheduler on Ada. Ada is one of the supercomputers. We have three: Ada, Terra, and Curie. Ada, being an IBM cluster, uses IBM scheduler, LSF. Terra is a Lenovo cluster, so we use like an open source scheduler there called Slurm. But a job scheduler, LSF, being a job scheduler, the basic idea of a job scheduler is that it basically manages processes, so on a shared computing resource. So Ada being a large supercomputer, we have a whole bunch of users. And these users, we have to have some kind of way to organize organize the resources so that everyone can get a fair shot at using the nodes and stuff. So that's where LSF comes in. So we're going to take a look at how to work LSF, basically, how LSF works and stuff like that. So without further ado, we'll go ahead and get going. If you have questions, feel free to drop them in the chat. I'll be monitoring the chat. Braden's also here too. Braden will probably be doing it more than me because I have to close this window every time so we can like see the screen. So ask your questions, and every now and then, if I see the notification pop up, I'll check in and clarify whatever needs clarification. Okay. So here's the general idea. We have login nodes where you log into the system, and then we have compute nodes where the actual work is done. So on the login nodes, these have the internet connection, so we can access them from wherever. As long as you're connected to the VPN. So like right now I can connect to the Time of VPN and then do the duo thing on my phone, approve. Now I'm connected to the VPN. So if I open up my terminal, I could SSH into Ada and I'd be put on one of these login nodes. The login nodes are there so you can write your job scripts and submit your jobs. And then once you submit your jobs, you actually submit them to the job scheduler. In our case, that's LSF. And then the job scheduler does all its magic and stuff and finds the perfect place inside the cluster for your job to run. So it looks at the resources that you request, typically how much time, how many cores, and how much memory you need for your job to run. And then given that information, LSF can decide to put your job on one node, maybe entirely on one node, or it'll put your job on one node and put someone else's job on that same node too. And that's how we kind of divide up the resource and let people use it. There's tons of compute nodes, like hundreds of them. And then also we have the shared file storage. So this down here is like your hard drives and stuff. The login nodes and the compute nodes both have access to the shared file system, which is right here. File systems and user directories. So from the login nodes, you can see all three of these. You can see the home file system, scratch, and tiered. The compute nodes cannot see tiered. So any data that you're working with currently, so your current data, that should be placed inside your scratch directory. So these are basically like, if you want to think of them as like separate hard drives, that's kind of how they are. They're separate file systems altogether. But the compute nodes can see everything in home, they can see everything in scratch, but they can't see tiered. So if you put a path to a file or data in tiered, if you put the data in tiered and then give the path to it in the job script, and we're going to talk about job scripts in a second, LSF will return a command, an error saying, "Hey, I don't know what you're talking about. I don't see that. File does not exist." Also, these aren't shared between clusters. So like Ada's file systems are Ada's files, and then Terra's file systems are Terra's files. Yeah. Okay, and so here's one more diagram to kind of just really drive home how this works. So when you're on campus, you connect to the network. Then from the network, you SSH into the login nodes. And then on the login nodes, you create a job, and you create a job by writing a job script file, a job script. These are just they're text files that you write out. Typically, what users do is they go to our wiki and they copy the examples we have there, and then they just modify the parameters. That's perfectly fine. That's probably how most users start out. That's how I started out when I was writing job scripts. And then once you have that job text file, you submit that to the job scheduler, in our case right here, LSF. And then LSF reads the script file that you gave it, and it decides on a queue to place it in. And then once your job goes to the front of the queue, it gets placed onto one of the compute nodes and it starts running. And then once it runs, you get some output, and typically in the form of mostly text files. That's basically how it goes. And then the output files are show up wherever, by default, they show up wherever you submit from. So if you submit your job from the Scratch directory, the output files just go to the Scratch directory wherever you were. The process stays the exact same if you're off campus. You just connect to the internet and to the VPN, just like I did up here. And you could do that by going to connect.tamwo.edu. So the batch job script is just a text file that contains Unix and software commands, and then batch manager job parameters. So I think we have one right here. Yep. So this is what a job script looks like. It's just a text file. And then up here in the top right corner, we see a little diagram which would show, if we could pretend this square is a node, and then each smaller square is a core. So on Ada, every node has 20 cores. So yeah, so this one's only using one core. So that's why that one little square there is green. But back to the job script. This is a job file. This is a serial example. So we're asking for one core on one node. At the very top, you'll see this this block right here. These are the necessary job specifications. These are required for the job to run. So you're gonna have to have all of these here. If you're missing one, like let's say if you're missing like a very important one, like the wall time, when you try to submit the job, LSF might tell you, most of the time it'll catch it and it'll say, hey, you're missing this parameter, we can't submit your job, error in job submission or something like that. Sometimes if you write a job script incorrectly, LSF won't catch it, and your job will be pending forever. It'll be in queue forever, in other words. And then in that case, you'll have to kill the job and then resubmit it, fix whatever issue and resubmit it. So sometimes you'll have to think about whether or not your job is pending because the resources aren't available, or because there's an error in your job script. But hopefully today, when we talk about job scripts, we can reduce the mistakes that you'll find, the very common mistakes that you'll make when writing these job scripts. The easiest way to do it is, like I said, to go to our wiki and to just copy paste all this text and then put it in a text file and then edit it. But let's talk about these lines. So this is just a text file, right? It's just a dot text or whatever. I typically name my Ada job files .lsf. That's just in my head. I instantly know it's an LSF file. And so the way the computer is going to interpret this is at the very top in blue right here, we see a double hashtag. The double hashtag is going to mean a comment. So actually, all of these hashtags mean a comment. But these lines right here that say hashtag capital V sub, these are the parameters. The technical term for them is a directive. So this is an LSF directive right here. And it's a hashtag capital B sub. So when LSF is given this file, it looks for the hashtag followed by a capital B sub. And when it sees hashtag followed by a capital B sub, it immediately knows, okay, whatever comes after this, I'm going to read as an argument and then use that as a parameter. So that's why you see the hashtags here. We use the double hashtags. This is just like us to make it easier on the eyes. The double hashtag means a comment. So if we had removed this hashtag and just had one hashtag here for necessary job specifications, it would still read as a comment. It's just kind of easier to if in our heads we can pretend that the double hashtags are comments and the single hashtags are B sub directives. So let's talk about these necessary job specifications. This first one right here, /bin/bash, sets the execution environment. So it's providing the shell. So we're saying we're going to use the bash shell. So when we connect to Ada, we log in through SSH, and we typically use a bash shell. So this line will always be the same. You don't want to change that. This next line right here, -J, sets the job name. So in our example here, we're setting the job name to example job 1. This could be set to whatever. Obviously, that one's important. Every job needs a name, but you could get creative. I've seen some people name their jobs pretty creatively on the clusters. So the next line, -W, is the wall clock. So when you submit a job, you have to provide a length of time that you want the job to run for. And this is the maximum, the absolute maximum job time that you want this job to run for. So in our case, -W 2:00 says, I want this job to run for no more than 2 hours. So if your job runs and it finishes early, so its execution ends early, that's fine, the job will finish. It will only take the full 2 hours if whatever program you're running, in this case, we're running my program.py, if your program continues running and doesn't return a result at the end, let's say like there's an infinite loop in here, it'll run all the way to 1 hour and 59 minutes and 59 seconds. And then as soon as one more second passes, the job will end, and it'll basically be like task manager killing your job, killing your process. And Ada, the job scheduler in Ada, LSF, will print out in your output, it'll say error wall clock limit reached, wall time limit. Yeah, so you'll get a wall clock error, and it'll say that your job, exceeded the wall clock. It ran to the wall. So if you see that, if your job hits the wall clock, I need to either check my code because my code should be executing in this time, or you need to extend the wall clock. But yeah, so this is the absolute maximum. The next two right here, pretty important, -N1, and then capital R span p tile equals 1. So these two values right here, the -N requests 1 core. So this is going to be total cores for your entire job. So this is a serial example. So we're using 1 core on 1 node. So some glossary key term information here. Remember, the node is like the computer, and then each node has 2 sockets for 2 CPUs, and each CPU has each socket has 10 cores, so 20 cores total. So Ada being a supercomputer, it's a collection of nodes with a whole bunch of smaller CPUs on them. So when we say 1 core and then p tile value is 1, we're saying I want 1 core and then 1 core per node. So in total, we're only asking for 1 node. These are very important, and your p tile value should always be on Ada no more than 20. So you can put p tile as 20, and that's going to say I want the entire node. I want you to put 20 cores on this node. That's valid. You might have to wait a little while because you're requesting an entire node, but that is valid. This n value right here can be larger than 20 because this is total node. So for instance, this could be 40, and you could say I want 40 cores, but I want to split it up between however many nodes, and then you do the division right here with the p tile value. These next 2 lines under p tile. So typically when I refer to these, I refer to n as the total number of cores, and then the cores per node I refer to as the p tile value. And then right here we have our usage value. And so our usage mem and -m right here, minus capital M, these these set the amount of memory. So on Ada, we specify memory per core. So what this value is doing right here, our usage mem equals 2500. We're saying we want 1 core per node, and then 2,500 megabytes per core. These 2 values should always match each other. So typically you'll want to put a memory value right here, and then you just match it in this -m. I think this is the default value for the -m. So if you were to omit this directive, it would automatically be set to 2500. But your job can see some interesting and hard to diagnose errors when these 2 values don't match. So just always match them. And remember on Ada, when we set our usage, we're setting memory per core or per process, same deal. So in total, we're asking for 2.5 gigs roughly. Do we have a question? So Kenna said, how can we figure out how many cores and cores per node we need for a job? Oh, I missed Ryan's question. I'll get to your question. One second, Ryan. Kenna, the answer is, what's the word I was looking for? It was on the tip of my tongue. It's mostly trial and error. So like you should generally have an idea. The easiest way to do it is to kind of run your job and then see how much memory you need. You don't know what errors you're gonna get until you get the errors. So you might want to start like with 10 cores and then request like half the memory. So like, 25 gigs of memory for the whole node, and then run it and then see if see what errors you get, stuff like that. It's a lot of trial and error, especially like getting the wall clock time down. So you'll just have to submit jobs, and it'll take a second. But once you submit a couple jobs, you'll get a feel for it, and you'll kind of understand. Okay, I need this code will generally execute well with 20 cores. If I just request a single node, 20 cores, put all those 20 cores on a single node, request all the memory, and then just run it and see what happens. And yeah, and it also depends on the job you're running. And so for Ryan, so you have a job script optimized for PBS. Is there a short way to change to accommodate to LSF? You'll have to rewrite the whole script from PBS. Mostly, so I'm not too familiar with PBS. I'm only really familiar with LSF and Slurm. But if you can get your PBS file and pull out, if you can provide it to us, we could probably run it to you. Actually, one of the other student workers wrote a nice script for easily generating these kinds of job scripts. So if you can get like these parameters, like how many cores, how many nodes, how much memory and stuff like that, how long, with that information, you could build a job file like this pretty simply. But if you need help doing it, you could send us an email at help@hprc.time.edu, and we could knock that out. I'd also like to work with PBS because I haven't had a chance to, so that's very interesting. No problem. Yep, and that's the email right there. Thank you, Braden. Okay, yeah, so the memory values, remember you set memory per process, per CPU. This is measured in megabytes, by the way, because that'd be ridiculous if we said 2,500 gigabytes or something. So yeah, this is measured in megabytes. Down here, these last two, -O, -E, these set the names of the output. In this case, we're directing the standard output and the standard error to two different files. We could, I think if we omit the -E, it'll all get routed to standard out. But yeah, so these are what these are going to be the names of the files that have your output. And then the %J is a variable for the job ID. So obviously, when you submit this to LSF, LSF needs a way to like track it, and it gives it a job ID. So yeah, it'll be standard out dot like 111112 or something like that. Those are pretty simple. Next little blocks are the optional job specifications. The three we list here are -P, U, and then the -B and N go with the -U. P sets the project account for you to charge. So when you submit jobs, you're charged SUs. We're going to talk about SUs and stuff like that in a later slide. But basically, the short version of it is when you apply for an account as a student, like me, I'm an undergrad student, right? So I applied for a basic account, and I'm given 5,000 SUs. And we can think of SUs as kind of like the units that the currency, so to speak. So when we submit jobs, LSF, or actually the account management system, AMS, handles the billing. It looks at your job script and it calculates how many SUs to charge you based off of how long your job is, how many cores you're using, and how much memory you're using. Takes those three factors and then assigns a value. You could kind of think of it as 1 core per hour is 1 CPU. Memory factors into there. I think it's actually 2,500 megabytes is also equivalent to 1 SU. In this case, this example right here, 1 core for 1 hour, or sorry, 1 core for 2 hours is going to charge us 2 SUs. So yeah, you're charged SUs. You can have different allocations. So to switch between those allocations, the one you want to charge, you'd put this, the allocation number right here. Then right here, we see these two lines. These are related to each other. B sub minus U email address sets an email address to notify. And then this line right here says, I want to be notified when the job begins. And this says, I want to be notified when the job ends. That's in case you're submitting a job that's going to be pending for a long time. Typically, if your job's going to run for like more than a day, you might see a slight wait time. Sometimes you'll see a real quick wait time. Sometimes it'll be a little longer. If you experience an abnormally long wait time, or if you're just very curious why your job isn't running, you could always email us again and we take a look at it. Sometimes it's because the cluster is very busy and there's not enough resources. Sometimes it's because there's an error in your job script that LSF didn't catch and your job might be pending forever. Not to scare you or anything, but that does happen on occasion, and you could email us and we could help you out. So after all these these hashtag BSub directives, down here we have the actual code that's going to get executed. So all the stuff beneath BSub is going to be executed as if you had just typed it into your terminal. So in our example here, we want to run this program, myprogram.py. And so the prerequisite steps to running this program would be to load Python 3.5.2, built with the Intel 2017A toolchain, and then you just /myprogram.py. So you need to remember to write. So all the steps that you would do to run your job as if you were typing them into the terminal, you would take those steps, copy them, throw them here. And then when you send this job file to LSF, LSF reads all this stuff right here, these two blocks, the necessary and the optional. It allocates your resources, and then it goes down here and it executes the code that you wrote in on the node for you, and then gives you your output named right here. So that was a lot. That's basically how it works in this example. So let's talk about some other important batch job parameters. Actually, we covered these. So -L is for initializing the job environment. Here, -W specifies the time. On Terra, yeah, you can specify seconds, but here, the format's going to be hours, hours, minutes, minutes. Or if you omit the colon, it's just minutes, minutes. -N is the number of cores for the job. P-tile, remember the maximum number of tasks to allocate per node. So P-tile is going to be your cores per node value. And these two sets the maximum amount of memory in megabytes. This is per core, remember, on Ada, per core. Okay, so job mapping. Was there a question? Are these similar for the other clusters? Yeah, so LSF, like LSF is a, what's the word? Proprietary software, I think. I want to say, yeah, pretty sure it's proprietary. It's owned by IBM. So the idea of a job scheduler is basically how all supercomputers do their work. It's never like a free-for-all, or I mean, shouldn't say never. I'm sure somewhere there's a supercomputer where, you know, the administrators, like, they just throw their hands up in the air and everyone does whatever. But on most organized computing, shared computing resources, you're going to have a job scheduler similar to LSF. LSF is used other places too. LSF is one, PBS is another one, Torque, and Slurm. I kind of like Slurm the most. I feel like I feel like Slurm is easier to use, or it's more I don't know why I like Slurm better. Maybe I just work on Terra more. But yeah, we do have a Slurm course similar to this Slurm job scheduling on the Terra cluster. But yeah, so this general information, you could use this on other clusters as well. This is just specifically like how we use it on Ada, but the same principle applies to other shared computing resources. Okay, so mapping jobs to cores per node on Ada. So in example A over here, we have 20 cores on one compute node. So these parameters would look like -N equals 20, -R p-tile 20. So you take 20, you divide by 20, you get 1. And so we see one compute node. This entire node's being used by this job. Example B over here, we're requesting the same amount of, it's right here, same amount of cores. So we're saying we want 20 cores, but we want 2 compute nodes. So -N equals 20, -R span p-tile equals 10. So we take the 20 divided by 10, we get our 2 nodes. And now the benefits of this is that we don't have to wait for an entire node to be open. So while these jobs would execute kind of the same, because they're both using 20 cores, example B might run faster, or might queue faster. It might run faster, as in like actually start running faster, not like time-wise of the job, because we're requesting less resources per each node. Now you could keep on going, as we see over here in example C, and divide it from 2 nodes to 4 nodes. But when you start doing this, you kind of start fragmenting the nodes. So you kind of see now how now we're requesting a quarter of each node, but we're requesting 4 times as many nodes as the first example. So when you fragment your nodes like this, your job will probably start running faster, because it's easier for the system to allocate smaller bits of resources at a time, as opposed to large chunks like example A. But now your job has to communicate between 4 nodes, and so that's gonna across 4 nodes is probably not gonna affect your job very much, but across hundreds of nodes, thousands of times for a job, probably will. And then depending on how much memory you're requesting per node, or sorry, per core, you might be fragmenting the node such that other users can't access these nodes. Because remember, we're trying to divide these nodes up by not only by core, but by memory as well. And I think the next slide, talks about memory. So I put this up here. It's always hard to find a place for this little thing. Okay, let's see what these questions were real quick. Okay. Yes, and all this information that we're talking about today is all on our wiki. The wiki has the wealth of our knowledge, especially on like LSF and ADA, LSF and Slurm. So all the stuff that we're talking about here is on the wiki. There's some quick start guides that you could find that just like run down in much more detail than this, because there's a lot. We try to fit all this like in an hour. So job memory requests. When LSF is allocating resources, we're allocating based on well, first is time, so we don't want jobs to overlap, and then after that we need to have the amount of cores available and then the amount of memory available, because if you have a core and you're going to use a core but you don't have any memory for the core, it's basically useless, right? It's like, what's it going to do? On ADA and LSF, we need to specify these 2 values, the ones that we said we're going to match, the -R usage, and then the -M process size limit. So these 2 should match. The default value is 2,500 megabytes, roughly 2.5 gigs per job slot. If these aren't specified, you should always specify your memory. You never want to just like go willy-nilly with it and let LSF decide how much memory you need. That's crazy. And to remind you guys, on ADA, most of the nodes have 64 gigabytes of memory. So because they have 64 gigabytes of memory, doesn't mean that you could request 64 gigabytes of memory for your job. That's because around 10 gigabytes, roughly 10 gigabytes, is used by the system. The system referring to the operating system, actually, like, keeping the computer alive. CentOS on ADA, and then also being used is LSF. LSF needs memory to run these processes. So the 64 gigabyte nodes typically have around 54 gigabytes of usable memory. So that means that your per process memory limit is going to be roughly 2,700 megabytes for a 20 core job. So if you're requesting a 20 core job and you're going to put that on one node, as in all 20 cores on one node, you're going to want to keep your R usage value, I'd say less than 2,700. Putting it right at 2,700 can be dangerous. So maybe like 2,600, 2,650 or so. And you'll be under that 54 gigabyte mark, and you should be able to get your job run on the 64 gigabyte node. If you absolutely need more memory than the 64 gigabyte nodes can provide, There are larger nodes. So we have 256 gigabyte nodes, but there's far fewer of them, like far fewer of those nodes. So your job queue time will probably be increased. To select those nodes, you use this parameter right here. So we're saying b sub minus r, because r is for our resources, and we're saying we want to select this resource. And what resource do we want to select? We want to select mem 256 gigabyte. We're going to see this line come up later when we want to tell LSF to select a separate resource. But yeah, so that's how you would specifically select a larger memory node. And then again, if you need even more memory than 256 gigabytes, first off, that's crazy, but not unheard of. There are even larger 1 or 2 terabyte nodes, but they have whole separate rules. And so the LSF side of it is just, if you're gonna select those resources, you would say minus R, select mem 1 terabyte or select mem 2 terabytes. Also, you have to put yourself in the extra large queue. So you'd say b sub minus q extra large. So what that's saying is you're telling LSF, put me in the extra large queue, and I also want to use these resources. That's pretty much that's all we're going to go in today, because we're trying to keep this more about LSF and not so much about Ada in general. But if you need help doing that, send an email. We could show you guys how to, because there are these super large terabyte nodes have some quirks that you gotta remember. Okay, so service units. When you are using LSF on Ada, you're going to need to specify these resources. You're going to specify how many cores, how much memory, how much wall time, and then whether or not you're going to use a GPU or not. If you're not going to use a GPU, you just don't say it at all, and then you don't use a GPU. If you're going to use it, you have to ask for it, in other words. When you submit your job, like I said before, you are charged SUs. So SUs are your service units. They're charged from your billing account. So to see your billing accounts on Ada, you would say my project. So when you type in my project, this is what the output will look like. In the first column, you see your account number, your allocation number. So allocation and account are essentially the same thing. I try to say allocation more often because account, people typically think of like, oh, when I log into, like your account is what you log into with your net ID and stuff. But your account can have multiple allocations. So in this example, this guy's Ada account has 2 allocations. One has a 10,000 SU balance and the other one a 5,000. Okay, a little less, 4,900. But that's what the output looks like. The other consumable resources are licenses. So you guys know that some softwares have licenses. They're like license restricted. So if the software you're using is license restricted, you need to wait until a license is available. That's pretty easy to kind of comprehend. The only issue there is the licenses are shared between all users. So if Braden is using 100 of the 101 ANSYS licenses, just to like use random numbers, and my job needs 10 ANSYS licenses to run, I can submit my job, but my job will have to wait until Braden's job finishes and releases his licenses. So we do have licenses. You can use these tools, license underscore status. It's a script that is aliased when you log in to the clusters. You can use this script to search for the licenses, and you can see how many are available. This is what it looks like. In this case, we see like there's 50 issued, how many are in use, and how many are available. And then the script has some other options like that. But if your job is license restricted, if your software is license restricted, you'll need to wait till the license becomes available. If you are working with license restricted software that we don't have on the cluster already, but you have your own license, typically we could work with that. You just have to send us the license so we can host it for you. So that's another issue to email us about, so we could work one-on-one with you. But if your software is license restricted and you only want to share it with your specific group of researchers, that's also an email. We could set that up, like private licenses and stuff. But those are the 2 resources. SUs, which you get when you apply for accounts on the cluster, and then licenses, which are shared between all users. And so you got to wait until other people haven't used all of them. Okay, so queues. Job submissions are auto-assigned to batch queues based on the resources requested. So again, cores, nodes, wall time, memory, etc. That determines which queue you're put in. So the queues are just the different lines for your that LSF uses to like organize the jobs. The big thing you're going to want to take away from here in LSF is that if you want to access a specific queue, you'd use this directive, -q and then the queue name. In this case, extra large, which is for the 1 2 terabyte nodes. So here are the queues on Ada. Oh, are you charged SUs for how long your job waits in queue? No, you're only charged SUs when your job starts running. So when your job's in queue and it's pending, we're gonna show you how to check on your jobs and stuff. You're not charged any SUs at all. I actually did not mention this before. So when your job starts running, let's go back to this example over here real quick. This example, this first one we saw, the serial example, the job is running for 2 hours. Let's say you submit this and myprogram.py finishes in 5 minutes. So we requested 2 hours, but it only ran for 5 minutes. So what will happen is you'll only be charged the difference between, or you'll be refunded, sorry, the difference between how much your job ran and how much you requested. So when you submit your job, LSF or AMS, the system will charge you for the worst case scenario. So it would charge you 2 SUs. If your job only runs for 5 minutes, it's only going to charge you 1 SU because you just used 1 core. It might not even charge you 1 SU because it probably rounds down or something. But you're refunded the difference. So it's always better to overestimate your time because you will get well, it's better to overestimate your time than underestimate it, at least, because you'll be refunded the SUs. And no, when you are pending, you're not using any resources, so you're not being charged any SUs. So back to queues, this is what the queues look like. There's quite a few of them. SN means single node, MN means multi-node. So single node, short, regular, long, extra long, and then multi-node, short, small, medium, large, extra large. VNC, which are GPU nodes for remote visualization jobs. The special queue, which is, you got to email us to get into that one. That's the queue for special jobs. If there's a special case scenario where you need resources that typically aren't available, or you need a combination of resources that are really hard to scrounge together normally, we could throw it on the special queue. But again, that's an email for us. And then the V100 queue for using the Tesla V100 GPU cards on Ada. Those are really cool GPUs, by the way. They're really cool. They're really big too. But yeah, so those are the names of the queues. They're divided up by wall time. So and then there's limits on how many cores you could use in each one. So like all these, we have a maximum of 20 cores, and then you have a maximum wall time for each queue. So if your job is like a 1 hour job and it's using 1 core, it'll probably be in single node short. So yeah, that's how it's typically divided up. This is a big table, which we're not going to go over entirely, but that's the idea. So BQs is the command on Ada for looking at the status of the queues. So this is kind of an old screenshot, but you see here, we're logged in on Ada 1 and we say BQs and we get all this information here. So what we're looking at here, the 3 most useful ones are end jobs, pending, and running. This is telling us how many jobs are running, how many are pending, and what the, end jobs is the total number of jobs. Pending is how many are pending, and then running is obviously how many are running, and then suspended. So this is how you could manage, how you could see the specific load of your queue. Your queue, like I said, is determined at job submission. So when you say right here, when you submit your job, you're given a queue. So to actually submit your job, in our case, we have example 01.job. This would be our text file. From the command line, we say b sub, and then we use this less than symbol, which kind of looks like an arrow. So you could kind of think of it as saying you're sending example one dot job to B sub. B sub in our case, when the command line is going to be lowercase when we're invoking the when we're invoking LSF. Remember, it's capital in our directives over here. When we're writing directives and stuff, we're gonna inside the job file we're saying capital. But this line right here is not a directive. This is a simple call to the scheduler. So B sub and then the little arrow pointing that way, and then the name of the job file. Obviously, the job file should be in your directory where you're standing and submitting the job. This is what it looks like. This is AMS saying verifying job submission parameters, verifying project account, checking to make sure you have enough SUs. And then it says account to charge, and it gives you the allocation number, the balance, and then how many SUs it's going to take. And then if you're successful, you see job, and then it opens these symbols, and then it gives you the job ID. So here's the job ID as assigned by LSF, and then it says your job was submitted to default queue single node short. So in this case, this job did not specify a queue, and LSF put it in single node short. So then you could go take that information and then run VQs and find single node short, and then see, okay, well, there's nothing running here, so it's probably going to run really quickly. To check the status of your job, you'd say B jobs. So B sub submits jobs, B jobs shows you all your jobs that are running. In our case right here, this job, which was the same job that was submitted, is running, and it says, gives a job ID, the status. If your job is pending, instead of run, it'll say penned, obviously. I think when your job is finishing, if you are able to catch your job in B jobs while it's finishing, it'll say like finishing or something. But most of the time, it's going to say either pending or running. The user, obviously, it's going to be you. The queue that it's running in, the name of the job, how many hosts, how many cores it's running on, etc. How many nodes, how many cores it's using, and then how long it's been running for, and how much time is left. The time left is the wall time. So whatever the value you set as the wall time, that's going to be the time left right here, and then it's just going to start counting down. So this time is not 100% accurate because your job could either 1, finish early successfully, or 2, finish early with an error, or 3, run the entirety of the wall time, and then obviously have an error at the end when it hits the wall time. So let's look at these next 3 slides. We have 3 slides of job files with some slight differences from our first very simple serial job file. This one is a multi-core single node job file. So we're requesting up here in a little diagram, we see we're still on 1 node, but we're using more than just 1 core. So here we're saying 10 cores total, and then 10 cores per node. So 10 divided by 10 gives us one node. And then we take this value right here, 2500, multiply it by 10, and that gives us our total memory. And this one's actually going to run for 6 hours and 30 minutes. So we see we're charged a little more SUs. I think the first job charged us like 2. This one's charged us 65. So we're being charged more SUs now, but the idea is the same. We just have more CPUs to run this job with. And then down here at the bottom, we follow the same steps where we set up our environment. So we load the modules and we run our program. There was a question. Let's see. Oops. Oh, yeah. Okay, so this one is multi-core, multi-node. So now we're using many cores and more than 1 node. So our diagram up here shows us 2 full nodes. So we're saying minus n equals 40. So 40 cores total, and then our p-tau is going to be 20. So we're saying take those 40 cores, and I want you to put 20 cores on each node. So we're using 2 entire nodes here. So now this job will have to communicate between these 2 nodes, and this will probably take longer than the first 2 examples to run. And then down here, or when I say to run, I mean just to begin running, not to actually finish. Again, that is highly dependent on your code. On I'm just strictly talking about the time it would take for LSF to put your job on a node and then actually begin running. And then down here we see we're charged much more SUs this time around. We're charged 960 because we're using every core on 2 nodes and then basically all of the memory on the node. So we're basically being charged for 2 whole nodes, and then we're also being charged for 24 hours because we requested 24 hours. Now remember, if our job, just because we ask for 24 hours, doesn't mean we're going to use it. If our job gets an error in the first like 10 minutes of it running, which would be really, really unfortunate, but it does happen sometimes, then you're going to be refunded like, 900, and you'll probably be refunded the entire thing because you didn't even go for an hour. So you'll be refunded a lot of these SUs, but when you first submit the job, similar to like how a bank puts a hold on your account when you are trying to pay for something with the card, AMS will do the same thing, and it's going to withdraw the full 960, and then when your job finishes, it'll refund the difference, but that's after it finishes, not before. So our last little example here shows us how to select a GPU. So the key difference here is we're just saying our select GPU. So just like we said that we would select resources like the larger memory nodes, like the 256 gigabyte or the 1 or 2 terabyte nodes, we use the -R for resource and then select, in our case, GPU, and then this will put us this will put us on a node with the GPU. To select a V100, it's similar. You specifically request the V100 nodes queue with those nodes, but that's the general idea. And then I did not include one for multi-core, multi-node GPU because it's pretty much the same as this. You have a large value here, and then this value, your -n value is divided by your p-tau value, and then that's how you find it. So other types of jobs are MPI and OpenMP jobs. When you're using a whole lot of, when you're parallelizing, I can never say that word, for running jobs running your job parallel programming. I can never say that word. Parallel programming your job. You'd use MPI and OpenMP. For visualization, so like you want to actually view your job, you won't use a job scheduler for that. So you could go to the portal .hprc.time.edu, visualization jobs, so like actually seeing the GUI, like a graphical user interface of whatever application you're running. You could do that through the portal. If you want to launch a large number of concurrent single core jobs, so a whole bunch of really, really small jobs, you'd use Tamu Launcher. Tamu Launcher could have its whole own little primer, which we might do if there's interest, I guess. So the short version of it is if you want to play around with it, our wiki, hprc.tamu.edu/wiki. If you go there and then search Tamu Launcher, all one word, you'll find this page. Specifically, it's at software sw:/Tamu Launcher. It'll detail how to do it. You basically give it a file with some commands, and it's going to launch single core jobs and then run those commands. And it can be used with serial and multi-threaded programs. It can only be used in batch jobs as well. Yeah. And if a job gets killed, you can resubmit the same job to complete the unfinished commands in the input file. So very, very nifty. So here are some commands for job submission and tracking. The ones that are important are bsub for submitting, bjobs list the jobs, and then to kill a job, you just say bkill. And then to identify the job to LSF, you give it the job ID. So you're given the job ID when you submit the job, and you can also find the job ID with bjobs from that little column when it comes up. And then to kill, bkill, and then the job ID. Bhistory shows information for a job when the job's running. So if you want to see specific information, you'd use bhist. But to have a more finer look at the resource allocation for the job as it's going, you'd use LNU, which stands for list node utilization. List node utilization is used while a job is running. So the job has to still be running. And this is what the output looks like. It shows us the host name. So these are the different nodes that the job is running on. And then the utilization, and then how many cores. So in our case, it's saying we were assigned 20 cores. It's using 97% of them. So that's how it's, you could follow how much you could follow how your job is actually running on the nodes. Keep in mind that these three values are here, temp, swap, and mem. These are, they refer to the available amounts respectively and not the usage per se. So for real detailed usage of memory, that can be a little harder. But if you have a specific question or need specific help, it's always easier to work one-on-one with specific jobs. So send us an email for that. This is just for showing. Generally, you could use this. This is what a lot of people use LNU. And LNU is also on Terra too. How can I get this slide? This slide, all these slides will be on the primer page. Braden will link it right there. Boom, I knew he would do it. So on that page, these slides will be posted later today. We'll push another change, and the PDF of these slides will be there. Also, all this information is also on our wiki, just not as neatly organized as a PowerPoint, but yeah, we'll be there. So lastly, check your SU balance. So after you submit your jobs and you start running a whole bunch of them, you're gonna be thinking, oh, how many more SUs do I have? You use my project, specifically my project, and then -L. That will show you this output right here, and shows you your accounts and how many SUs you have left or having your balance. And then you could change the default account, but the B sub, the LSF directive to change the allocation to charge is going to be -P, but that is an optional specification. Okay, job environment variables. When you submit jobs to LSF, LSF has some environment variables that are set by default. So these are a few of them. LSB job ID gives you the job ID. You can also get the directory from where the job was submitted from. You could get, oh, and then Scratch is just, it's always there. Scratch user, your net ID, and then the temp directory, which is work, LSB_job_ID.tempter. So these are always set. I think there's more, but these are kind of the most common ones. Obviously, LD library path gets passed around too, that environment variable. But these are pretty common, so decided we'd list them there. And then Tamu batch. I had mentioned Tamu batch earlier when we had the question about PBS. Tamu batch is the tool for making these job scripts. So if you want to try your hand at that, and I think I should put like an asterisk here and say like, yeah, this is Tamu batch is it's really new, so it's kind of like in beta. I was playing around with it and I found a couple errors, and I was talking to Kyle, who wrote the script about it already. So feel free to use Tamu batch, give it a shot, and if it breaks anything or if you can't figure it out, let us know, and we could work with you one-on-one. But we do want to get more people using Tamu batch because it's really really good getting that feedback on it, and that's a very helpful tool for building these jobs. And then to plug our portal, so if you need to use Ada or Terra, the portal's there, and you can log in, and you can actually compose job scripts. So you could build those LSF files from the job composer on the portal, and then you can also launch interactive GUIs and stuff. But I think that's all I've got for LSF on Ada. So I'll stick around if anybody has any questions. But oh yes, also fill out this little poll, please. It's over here somewhere. Yeah, that would be very helpful. I will stick around for about another 10-15 minutes. If anybody has any questions, I will be here to answer them, and Braden will as well. I'm going to go, and I'm going to actually allow you guys to unmute yourself. So feel free to unmute yourself and ask a question, or type it in the chat. Either way works.